Hello, everybody, and welcome back to another lecture in Geography 341, Weather and Society. I'm Dr. Zach Hilgendorf, and today we're going to be talking about frontal systems. You might notice I'm in a bit of a different locale than my normal office that I lecture from. I'm currently at the American Association of Geographers Conference, and I'm recording this on the road. So I don't have my same studio quality mic that I normally use and all these extra things, so bear with me. It's only going to be for this one lecture here. So let's go ahead and dive into it. First off, I want to acknowledge some of the referenced materials that I used. Professor Ian M. Brooks, University of Leeds, and Dr. Eric Snodgrass, University of Illinois, Urbana-Champaign, I used for a number of the slides here. There's some really great graphics that I used. I just wanted to call that out and give them credit for their really, really effective slides. So, fronts. Now, what causes air to rise? We should know this by now. We've talked about it, these lifting mechanisms, right? Orographic lifting, so something being forced up and over a topographic barrier. Frontal lifting, which is what we're going to talk about today. Horizontal convergence, so converging winds at the surface, a low pressure system at the surface with winds rising and diverging at altitude. And then localized or free convection. So all of these different things have to deal with heat, pressure, and differences between air parcels, right? So we're going to talk about frontal lifting today. It looks like this, right? So we maybe have a colder air parcel and a warmer air parcel. That colder parcel is denser, that warmer parcel is less dense. This is what we would call a cold front, right? So as that cold front is pushing in, this parcel of air is moving. It's basically forcing that air up. So this colder air, this denser air, is forcing that warm air up. As it does so, meteorological things happen. We'll talk about that here in just a few slides. But this is opposed to a warm front, where you've got this less dense wedge of air pushing into this denser air. The warm air is obviously lifted. It is less dense, so it rises, whereas cold air does not. And that's a warm front, right? So fronts are an interesting concept. So the term was actually coined in World War I by Norwegians. This is basically an analogy to battle fronts. If you think of World War I, the Eastern Front, the Western Front, that was kind of the idea is you'd have this front moving in and kind of like a front of troops or the troops moving into an area. So it's basically just describes the boundary between two air masses. You've got a region of significant horizontal gradients in temperature or humidity. So if we think of it, we've got two separate parcels of air that are very different in one way, shape, or form, whether they're warm and moist air, cold or dry air, etc. So they're different. So that's how we think of it. We separate it by fronts. So as a front moves in, that's our way of saying that an air parcel of a different type is moving across the surface. They're typically 100 to 200 kilometers wide with very sharp transitions. Typically 100 to 200 kilometers wide. Very sharp transitions are uncommon. You see this kind of gradient. So they are our dominant feature in the mid-latitudes. They're associated with low pressure systems, so mid-latitude cyclones, extratropical cyclones, or depressions. Their movement is responsible for much of the day-to-day weather variability that we see. And in North America, we have many different types of air masses with frequent frontal passage, and that's why we have such variable weather. If we think of our position in Eau Claire, highly variable based on whatever's going on across the United States. If we look at what is going on across the United States, we've got these kind of typical air parcels that we would see. So very cold and dry air are capital A, continental Arctic air. We've got maritime polar, cold and moist air masses over kind of the Hudson Bay area and in the kind of Gulf of Alaska off the coast of British Columbia region. We've got continental polar, so cold and dry. It's air that is, kind of being impacted by the Arctic jet stream or this colder air at the higher latitudes, but it doesn't have any dominant bodies of water to draw moisture from, so it's very cold and it's very dry. We've got kind of these typical high pressure systems that set up off of our coasts that are pretty consistent based off of just kind of how these air masses are setting up. And we think of that 25 to 30 degrees north and south latitude. That's kind of right where those are lining up. We think of kind of our Hadley cell circulation, right? So we've got these high pressure zones kind of aligning with that. We've got maritime tropical. So this is warm and moist air masses. We see that off the Baja Peninsula and in kind of the Caribbean, Gulf Coast area. And then our continental tropics, so the interior, warm and dry, again, like Texas, north central Mexico, Utah, Arizona, Nevada, that type of region there. Very warm, very dry air masses. So let's kind of dissect a warm front here a little bit more. So basically what happens is you've got warm air that's flowing up and over a denser air mass. Now, compared to a cold front, this is the inclination of the frontal surface is very shallow. So 0.5 or 1/2 to 1 degree. So we're talking about the kind of the angle of that oncoming slope. The approach is usually signaled by high cirrus clouds. So if we think back a little bit, we were talking about clouds and how we can use clouds to interpret weather. And we talked about cirrus clouds and how noticing cirrus clouds, especially if they're followed by other types, cirrostratus or altostratus, that's a really good indication that some type of meteorological phenomena is impending. So its approach is signaled by a high cirrus or cirrostratus. The cloud base is going to start lowering as that front approaches. So you go from your cirrus clouds, your high altitude clouds, down to altostratus, down to nimbostratus, these, full encompassing, very, the ones that you don't see the sun, right? Or any discernible difference between the clouds. They're kind of a single consistent blanket, if we think of that stratus term again. Rain starts ahead of the surface front. It is widespread and it is persistent. So the front, if we look here, grab my pen tool here. So the front might be here. You can see where I drew that, right? That's that leading edge of that wedge. But notice we've got rain all the way over here. So what's happening is as you're forcing that air up and over that colder air, so that warm air up over that colder air, what's happening? Well, air is rising, it's cooling, things are condensing, you're getting cloud formation, and you're getting rainfall. So here, because you've got this very shallow gradient, you're forcing that up, you're getting a much broader area that's really being impacted here with that warm front impending. And then you usually think of these as kind of your longer term, I'd say sometimes multi-day drizzles. And then behind that, you've got a warm front. So here you've got this warmer air that we see here, that as that front pushes through, then you're going to start seeing nicer, warmer temperatures relatively. And then the skies are going to clear up pretty quickly after the passage of that surface front. So once this position here, again, this one over here, once this moves through, you're going to see pretty quick clearing of your skies and your rain will kind of subside. So we can look at it like this. So we've got this warm, moist air from the south pushing north, raises over the cool and moist air masses that you see here that are sitting to the north and east of the warm front. This type of atmosphere is generally stable because the region of lift corresponds to a region that has cool temps at the surface and warm temps aloft. A stable inversion like sounding is what you would see. Now a cold front, on the other hand, we see that dense cold air pushes forward into the warmer air, which is forced upward. This is much steeper, so it's about 2 degrees is the kind of inclination plane for a cold front. So here, what you might have is these deep convective clouds that form above the surface front. Heavy rain in a narrow band along the surface front, and then behind that front, the cloud base lifts and eventually clears. So what's happening here is you've got this warm air that's being rapidly kind of shunted up, right? You've got this really steep gradient with the cold air wedging its way through. If we look here, roughly, perhaps for this example, 70 kilometers wide, 200 kilometers wide is where kind of the full extent, if we look at the full development of that cumulonimbus cloud there, that you can have, 270 kilometers or so. And in this case, what we're looking at, what we're dealing with is anvil clouds, right, or cumulonimbus clouds, these high, rapid vertical development, lots of kind of turbulence and churning and energy within this system. That's where you're seeing maybe your thunderstorms, maybe your tornadoes. Some of your really big, kind of heavy hitting storms are coming from cold fronts pushing into a warm front, cold air pushing into a warm air, cold front, rather than vice versa. So these are a lot more dramatic than a warm front would be. You can think of it like this: cold, dense continental air from the north meets the warm, moist, maritime tropical air from the southeast. Usually a hotspot for severe weather, like I said, because this moist tropical air is generally unstable and moist, and the front acts as the lifting mechanism to complete the ingredients needed for thunderstorm development. So the next one is a stationary front. So there is no fundamental difference between the air masses on either side of the warm or cold fronts. The front is defined by the direction of motion here. So when the boundary between those air masses does not move, it's called a stationary front. It's stagnated. Wind speed is not zero, and there is still individual masses that are still moving, but the boundary does not move. So this can be associated with significant precipitation. So here you kind of stagnate, and then you're just raining and raining and raining. You can get consistent, long drizzles with a stationary front. So in practice, a front is defined as stationary if its motion is negligible on a synoptic chart, meaning the front's moving less than 5 knots or about 2.5 meters per second. And we get into occluded fronts. Now there are two types here. In general, cold fronts move faster than warm fronts, and sometimes can catch up with a warm front ahead. So when you have that happen, you have an occlusion or an occluded front. There are two types, warm and cold, depending on whether the air behind the cold front is warmer or cooler than the air ahead of the warm front. The occlusion is part of the cycle for frontal development and decay within mid-latitude low-pressure systems. So we can see that example on the side there. So from A to B to C, notice these transects going from A to A prime, B to B prime, and C to C prime. That's what you're looking at down here. So A is all the way down here at the bottom, and then B and C and so forth. So at A, you notice there's kind of cold air mass over here, a very cold air mass over here. So very cold air mass, as we look at the top again, over here, cold air mass over here. We notice we have wind directional differences. So this is flagging from the northwest versus flagging from the southeast. So what's happening here is as we get closer and closer to that occlusion, so if we look at B, where that occlusion is, that warm, cold air is, or sorry, that very cold air and that cold air are starting to wedge together. That warm air is being moved up. Remember, warm, less dense. And then we see that happening even more once we get to C, like within that occlusion. So very cold and cold air is right next to one another. This is what we call a cold occluded front. We'll take a little bit more look at these here in just a second. But your warm air is kind of forced upwards, and as it does so, you get condensation and precipitation. So here is a warm occlusion. So in both warm and cold occlusions, the wedge of warm air is associated with layered clouds and frequently with precipitation. Precipitation can be heavy if warm, moist air is forced up rapidly by the occlusion. So here we're looking at kind of a couple things. Notice that we've got kind of overlapping of the cool air, which is slightly less dense than the cold air, which would be denser, which is denser obviously than the warm air that is being forced up. So you can see right at that edge, we're getting, decent rainfall right here. Right, so that warm air is being forced upwards at a variable rate, and as it is doing so, you're getting it precipitation starting to occur. And we've got a cold occlusion. So in this version, you've got kind of that warm air, or sorry, that cold air forcing into the cool air. So in one, with the direction of the movement, that cool air is going over the cold air. In this one, the cold air is forcing into the cool air. Kind of similar if you think of it to a warm front and a cold front, but here we've got similar air masses, and that warm air, that kind of third parcel, is being forced out of the way. Here you can have a bit more substantial rainfall because, again, you're forcing that air up much more rapidly than you would if you were with a warmer occlusion. And we can see, and we're going to be able to interpret these here, and that's going to be coming up probably in the next week or so, or in some of the next lecture sets. But you can see there is a ton of different stuff going on here. So we notice there is an occlusion. I'll try to sketch it out with something that would make sense here. See if you can actually see this. So we can see there's an occlusion right here. And what's going on? Rain and thunderstorms within this area. We see this massive cold front pushing from all the way down here in Arizona, all the way through to Quebec. We see another cold front from over Seattle, but we see that it stagnates here in Vancouver area a little bit. We see a bit of a warm front kind of pushing up from South Carolina into the Pacific right here. That's being part of that occlusion, obviously. And then we see another bit of a warm front from Quebec down to New Brunswick area. So we can see here this is just one day. This is November 28th of 2022 that I pulled this out. And you can see there's a whole lot of dynamism going on across our country at any given point, from snow that we see in Montana, Idaho, Wyoming, Colorado, parts of North Dakota, to thunderstorms that we see in Pennsylvania and Ohio, kind of that eastern seaboard region, to just simple rain in Missouri, Illinois, Michigan, Pennsylvania, up through New Hampshire, and then mixed precipitation. So based on the location of these fronts and what's going on with these different frontal systems, that's what's forcing our weather and our meteorological patterns to occur. So you can go to that link that I provide down there to kind of see what it looks like for a given day. I think it's one of the links that we use for our weather journals. But that's going to be kind of what's coming next. So there's a few different things here that there's one particular that we didn't talk about, troughs. We see here, these are these kind of low pressure, elongate low pressure zones. We'll kind of touch on those going forward a little bit. But that is all for this video. Just a quick recap, we talked about warm and cold fronts, stationary fronts, and occluded fronts, so warm occlusions and cold occlusions. Coming up, we're going to start moving into, I think, some more of the interesting and some more of the fun things where we're actually looking at mid-latitude cyclones, tornadoes, hurricanes, cyclogenesis, all of these different things. So understanding how these weather patterns are translating to meteorological phenomena that we see and experience throughout our year. So with that, I hope you enjoyed the video, and we will see you in the next one. Thanks.